Hi, everybody. Welcome to GAAC. Quick before we start, just want to remind everybody that we have a star party next Saturday, a week from tomorrow, next Saturday, August 16th. So if you can make it to Halbert Point, please do so. Yes.
What time does it start?
What time does it get dark?
9 o'clock or so.
All right, so tonight's speaker is Abigail White. She's a recent grad of Wesley College in math and astrophysics, or astronomy, sorry. And she's working in the Harvard University Department of Astronomy under Charlie Conroy and Daniel Fabricant to uncover the nature of dark matter. So please welcome Abigail White.
Hi everyone, I'm so excited to be here. Thanks so much for having me. I'm glad I could make the trip up from Cambridge, so thanks for the introduction. Yeah, I'm a third year PhD student in the Harvard Astronomy Department, working on instrumentation. So I'm going to talk tonight about both the science behind what I'm doing, but also a little bit more the technical side and telescopes and how we're actually going to do that. So title of my talk is Seeing the Unseen with VIA. All right, here we go. I'm going to start a timer so I don't go too much over. Okay, I'll talk a little bit about my journey just briefly about myself. So I grew up in Pennsylvania in a town called Reading, Pennsylvania, hometown of Taylor Swift. Yes, we're very proud. But I attended college not too far from here, Wellesley College. It's a historically women's college outside of Boston. And I came in as a math major. I did long division with my grandpa for fun growing up. I always just liked numbers and math. But I had to take a science class for my science distribution requirement at Wellesley. It's a liberal arts college. I was really dreading it, to be honest. I didn't have great experiences with science in high school. I much preferred my calculus classes. But I took this astronomy class, and I don't know, there was something really special about it. I just had a great time. And I have this image that I took of a study sheet I was making for an exam. And you can see I just had way too much fun with the study sheet for an average student who was just trying to pass the class. So this is about stellar evolution and what happens to stars depending on their initial mass. So I just think I look back on this picture with a lot of fondness because it just, you can tell that I was really excited about it. So I took astronomy and I thought nothing of it. I was glad to pass the class and move on with my journey. And then the pandemic happened. So I was a sophomore in college when this happened. I got sent home. So I was staying at home in Savannah, Georgia, where my parents live now. And I decided to take another astronomy class because my study abroad plans had been canceled. And I thought, well, nothing better to do in these times than add a second major. That's what people like to do, right? So from my desk in my room in Georgia, I was able to operate Wellesley's 0.7 meter plane wave telescope up in Wellesley on campus. And I imaged this globular cluster, M13, for a school project. And I just had a really good time with it. And that class really showed me the parts of astronomy that I liked, which was using telescopes and making pretty pictures. So after I took that class, I decided I was just gonna dive headfirst and give the astronomy thing a shot and see how far it takes me. So I graduated, woohoo, from Wellesley. So this is our observatory there. I highly recommend visiting if you have a chance. They do public nights every so often. It's a historic 12-inch refractor. And also at Wellesley, I got to learn about the history of the women that passed through the college. One that's very famous, Annie Jump Cannon, who's responsible for the classification of stars and how we group them together. So she literally sat at the same table and in the same room that I did studying for my exams. So that was just really special. So I really loved learning about that. And I then continued on after school. I took a one-year gap year and did a post-bac research experience, actually at Harvard, the CFA, building instrumentation. And that's where I just really loved the hands-on work. I honestly think it was being home for COVID that made me realize how much I did not like sitting at my computer all day. I wanted to be working with my hands. I wanted to be in person with people and collaborating on projects. So I think that just really showed me that I wanted to head into instrumentation. So that's a little bit about my journey, but that's not what you came here to hear about. We came here to hear about what is this unseen I'm referring to, and how are we going to measure it? How are we going to see it? So I pose a question. You can think of it to yourself. What is the universe made of? You might say stars, galaxies. You might say my dinner or my dog. And those are all valid answers. And they all have one thing in common, which is that they're considered normal matter. The other reason I loved astronomy is because I found it very humbling and unifying. So this fact I learned, and this was probably the most humbling thing, which is that this normal matter that I'm talking about only makes up 5% of the mass energy content of the universe. So some of you may have seen a pie chart like this. So all the things I mentioned are in this tiny 5% slice right there. And that's not a lot. So what else is the universe made out of? Well, this stuff called dark matter and this stuff called dark energy. And I wish I could tell you more about it, but the truth is that we just really don't know what's going on. We know that dark matter has mass, and it interacts gravitationally with things, but it doesn't collide with normal matter. It's collisionless. And dark energy, we know even less about. So I'm scared of dark energy, so I'm just going to stay away from it for the time being. We're going to focus on the dark matter aspect of things. So this is what I'm going to focus on, this pie slice here. 68% is a little bit daunting, but 27% I think we can handle. So dark matter, what do we know? What's the history? So it was first discovered in 1933 by Zwicky, and he did this by observing the Coma galaxy cluster, which is here. This image has thousands of galaxies in it. It's like the largest galaxy cluster that is known. And this image, you can measure how fast the galaxies are moving, and based on those measurements and what matter you can actually see, those speeds are way too high. So there must be something that we can't see that's actually holding them together. It's pulling them together with the gravity. So there must be something there. And that question kind of went unanswered for a little while. He coined the term dark matter because we cannot see it. So then in the 1970s, Vera Rubin, a female US astronomer, took measurements of stars orbiting galaxies. And what she noticed was that as you went further and further out in the galaxy, stars, their speeds, they picked up for a little bit and then they plateaued. So as you got further out, the stars kept moving fast. They didn't kind of decline as you would expect as you're having less stars and less gas, less dust as you're moving further out from the center of the galaxy. So that was really puzzling. And the reason for that is, well, they must be moving fast because of some gravity. So it was theorized that dark matter was the reason for those continued high speeds. So despite nearly a century since Zwicky first coined the term dark matter, we still really don't know what it is, other than it must be 5 times more abundant than ordinary matter. We know it's much, much more massive. So what could dark matter be? Well, theorists really like this question, and they like to theorize about many ideas. So there's no shortage of them. And if you can't read the words, don't worry about it. This graphic is just to show you that people are busy at work trying to come up with explanations for what this stuff could be. The problem is when you can't see this stuff and you can't make it in a lab, it's really hard to narrow this field down. You can't get an idea of, okay, this is untrue because of this reason or that reason. You can't cross things off necessarily from the starting point. So there's no shortage of ideas. The theorists are happily giving us many things to test. So the question is, well, how do we test this stuff? How do we get a better sense of what's going on? So there's kind of 2 main ideas here that have some nice pictures. They might not show up as nice on Zoom, unfortunately. But on the left, you're supposed to be seeing kind of these small clumps of dark matter. So this is one of the more popular theories of dark matter, cold dark matter, if anyone's heard that term before. And this is a theory that says, oh, maybe it's some massive subatomic particle. And we don't know what kind of particle, but it's has some properties like this. Or could it be more like a wave? And it's kind of hard to see on this picture, but if you look on the outskirts away from the orange more into the pink, you can see that the right-hand image is a lot more smooth. There's a lot less clumpiness going on. And on the left, there's a lot more clumps that are together. So there's these 2 kind of competing ideas. And this is actually on the scale of kind of the Milky Way and beyond that. So the bright orange part at the center is supposed to be where the Milky Way is, where our galaxy is, and then extending far out from the galaxy. So I hope it might lag a little bit. It's nice and smooth over here. If you look on my laptop screen. But this is a simulation of that popular dark matter model that I mentioned, CDM. And you can see here all these small particles that we call subhalos swirling around the galaxy. And the colors are representing different masses and densities. So you can see it's chaotic, but we can't see any of this. So this is all just theory. This is what computers tell us might be out there. So how can we verify that that picture is true? Well, we don't know what dark matter is, and it doesn't collide with particles that we're familiar with. But we do know that it interacts gravitationally. And we've used gravity as a tool for discovery for centuries. So we actually, in 1946, discovered Neptune not by seeing it, but by basically dropping something of its mass and size in to explain the anomalous motion of Uranus. So when we did that, the orbits made sense. So this concept of using gravity is not novel. We've been doing it for a long time. So in come these new things called stellar streams. And this might be new to most of you in the crowd. It was new to me when I started grad school. So these are these filaments, these thin filaments of stars that are orbiting the Milky Way, as pictured here. So this is the Milky Way on the right. You can see where we are right now. We're kind of off to the side there to the right. And these were first kind of theorized in the 1970s. So this idea that you could have satellites like small galaxies known as dwarf galaxies or globular star clusters kind of come in the Milky Way, like absorb them and basically capture them and then have them orbit the Milky Way. There was also this idea that yes, you have these clusters and dwarf galaxies, but over time, the universe is very old. Gravity alone can kind of pull them apart and produce these tails. So that concept of gravity being the only one that's able to do this kind of emerged in the 1970s. So it took us about 25 years later to actually see this in real life. So the first stellar streams were discovered in 1995. This was a Sagittarius stream. So if you're familiar with the Sagittarius dwarf galaxy, this is the stream that is following around the dwarf galaxy. You probably, I don't even think you could probably see this with the naked eye. You have to basically use data that allows you to see the motions of things to really make sense of it. And also PAL5. These are two big well-known streams. These are the first discovered. And that's kind of what they look like. This artist depiction, they try to put their artist flair on it, but that's not too far off in the picture. And I'll show you some pictures of some great ones soon. So this is a really nice video. It's a website that's available. Sorry, it's kind of small on this screen here, but you can see all the little colorful streaks. Those are all different stellar streams that we know exist today, observed and confirmed. So we only knew about a dozen streams before 2018. So what changed in 2018? Well, the Gaia satellite, which was launched in about 2013, came online, and they were able to release a bunch of data, giving us the proper motions of all these stars around us and in the galaxy. So by doing that, initially with streams like the Sagittarius and PAL5 stream, all you had was really your eyes. You had to linearly kind of detect over densities of stars around each other, and then confirm maybe big distances and other things that, okay, yeah, it's vaguely in the right spot. But with proper motion data, what that allows you to have is you're allowed to see co-moving stars together. So we're able to, instead of just to visually try to take a picture, we could just measure velocities and then say, okay, yeah, these stars are moving together. We can check distances. And we're also sorting by like metallicity, if you guys know what that is. That usually is basically measuring, as astronomers, my boyfriend is a chemist, so he cringes every time I say this, but as astronomers, we consider everything other than hydrogen and helium a metal. Heavier in the periodic table. That pains him, but it's the truth. That's what we do. That's what we do. So we measure how much of those metals, like iron, are in stars, and that determines their metallicity. So it's just like a ratio of how much like iron you have compared to something else. So anyway, so you can sort stars by that, and typically stars that were born in the very early universe, they only had access to those really fundamental building blocks of hydrogen and helium. But as stars, stars explode and they create these more complex elements and everything, then they can have access to these more metal heavy stars. So if you sort by metal core, they're old. And you also notice that these streams are far away from the galaxy. And that's because it's less chaotic out there. There's less stuff going on, so they can stay intact. They're kinematically cold, as an astronomer would say, which just means that there's not a lot of motion going on. They're just kind of hanging out there. So when Gaia turned online and we got this data released in 2018, it allowed us to discover more than 100 of these streams off the bat, which was really, really exciting. So this is just a visualization of all those streams that have been discovered and confirmed. We expect this picture to get even more populated with LSST or Vera Rubin coming online, which just shared those incredible first light images a few weeks ago. So I'm very excited to see what LSST is going to bring, but this picture should get a lot more exciting. So just taking a little step back, explaining a little bit more about how you get these objects. It's the same physics that explains why we have tides on Earth, so these tidal forces. So in this case, on Earth, we have the moon that exerts some gravitational pull, and this makes the oceans, which are more susceptible to stretching and pulling, to kind of bulge out from the Earth. And as we're sitting on the surface of the Earth and it's rotating, we go through these high and low points of the bulges. That's where you get the high and low tides from. So this same thing happens if you replace the Earth and the moon with the galaxy and a globular cluster. So the galaxy is exerting this tidal force on the sphere of stars, and the part that is closer to the galaxy feels a stronger gravitational force than the far side. So that disparity causes it to stretch out and form like a nice tidal stream. So there's a beautiful video courtesy of ESA that shows you this happening in action. And this is a nice, 30-second video, but this process takes billions of years to happen. So you can see, the cluster starts to turn more into like filament, stellar stream, if you will. And this is a real stream actually that they were able to model the data for.
Are they going through the plane of the galaxy or past it?
They're going, they'll like touch it a little bit, but they're not, if they basically go into where there's a lot of like gas and stars and other dust, then they'll get perturbed too much and then they wouldn't be able to stay in this like nice stream format. So they're far away from where that gas and dust are, which if you know, things that are far away are really hard to see. So we need to go super faint for that. So as I promised, this is a real image of a stellar stream. This is Cal 5. This is one of the first that was discovered. This was discovered by Anna Venanza, who is the PI or principal investigator of the project that I'm working on. So it's really cool to see that her work as a postdoc is now, we're going to even build further upon that. So I talked about dark matter and I talked about stellar streams. But how could they possibly come together? Well, as I said, these streams are really far from the galaxy and they're kinematically cold. There's not a lot going on. They preserve that initial velocity content that they were born with. So they're really sensitive to gravitational disturbances. So if something really massive came along, the stars would be attracted to it and their velocities would change. So we know that dark matter subhalos are predicted to be pretty massive. So this is a video. Sorry, it's going to lag. This is just showing you kind of what that would look like. So here we have the Milky Way. Here we have the stellar stream, which we can see. We have a dark matter subhalo, which we cannot see, but we're modeling as this glowing orange dot. It interacts with the sphere. It doesn't collide, but throws off the gravity, throws off the velocity of all the streams, and it punches a hole in the stream. And we can observe this. We can see the stars doing this in real time. So it's going to go back. We're going to watch it again. Here comes the stream. Here comes the dark matter. Crosses paths, affects the velocities, and boom. We have a hole punch there.
Are they shepherding it like the moons and Saturn's rings?
I'm not sure what you mean.
Little moons and Saturn's rings shepherd little sections of
like
the
they
rings.
carve out?
Yeah.
Yeah, so they're not colliding at all. So there's no collisions happening here. It's just the velocities are being affected by this really like it's a million solar masses object that's tiny that's coming through. Oh my gosh, that will make you feel a lot.
It's kind of stirring them up, that's it.
Exactly, it's just messing things up. It's like a little bit of chaos. And these things they're just floating out far away from the galaxy, you know, not a lot's going on, they're happy there, and then something comes along and boom, it's crazy, it's chaos. So this is a better picture of what we hope LSST will allow us to see. So this is strings that we already know of, but also a bunch of predictions of strings that we expect to see. So if you think about this picture, at the same time with the dark matter prediction picture, you can see that if you can observe enough of these streams and see enough of these interactions, you might get an idea of, is this picture clumpy? Is it smooth? Are we seeing no interactions? That tells us something. If we see a lot of interactions and it's distributed, you could do statistics and figure out like, what is the density of this stuff? Where is it? Where all is it? So that's kind of the concept of the science that's going here. So that all sounds great. And you all believe me, because you know I'm here. And I'm in school, so I wouldn't lie to you, right? But if you're like me in my classes, you might be wondering, how are you going to do this? How does this work? There's telescopes, and you're telling me we have to measure the motions of these stars. How's that going to work? So that's where I really love to sit in my research and my contributions. So we have great team members that made all those pretty videos and make all those observations and do all those great measurements. But I'm here to make their dreams a reality and build things that are going to enable us to do this. So this is an image of the MMT telescope in Arizona, just looking out in the night sky.
When you trail off, I can't record your voice.
Oh, okay. So I'll talk and then turn. Okay. So a little bit of a lesson with something that's important, that's something we use a lot in astronomy, is spectroscopy. So that word might sound a little scary, but if you've ever seen a prism or held a prism in school, that's exactly what I'm talking about. So that is enabling spectroscopy. So this prism on the left is one of the key mechanisms for how you do this. So you have sunlight coming in, and then the prism has properties that basically the light comes out in different wavelengths, it separates it by wavelengths. So you see a rainbow here. So when you look at the sun, it's just white. But when you separate it by wavelength, you can see all the colors that are composed actually in that light. So another fancier version of that we use a lot in astronomy is called diffraction gratings. So these are special types of prisms, basically, that have these grooves etched in them, such that you can get the same effects as a prism. I won't go into too much detail. But you might say, okay, that sounds really complicated. I've never interacted with that before. Not true. A CD is an example of a diffraction grating. So these have grooves in them, and if you see, like, if you've ever seen rainbows and stuff when you're holding a CD, that's what a diffraction grating is doing. So I have to say, I do know what a CD is. So you don't have to worry. I have held them before and used them. So it might be the last generation, but that's an example. Okay, so how is that actually used to do the science we want? Well, you can use it in different ways. So a lot of times when people are taking pretty pictures in astronomy, they're using emission spectrum, which is the center part of the image here. And that is basically when different molecules, they have reactions with photons and they're cooling off and they're emitting these specific wavelengths of light. Specifically, if you see an image and it's red, typically that refers to like H alpha, that's a hydrogen transition that's happening. But basically, if you isolate those wavelengths and you take an image in that wavelength and expose, and you get to see things that you wouldn't be able to see with your naked eye. So typically that's what emission spectrum are used for. But absorption spectrum are kind of the reverse of that, where you have a broad source of light, but there might be stuff in front of that light that is absorbing the photons and stealing away certain wavelengths because of the different chemicals that are composed in that gas, which is kind of what's shown here. And stars have that same kind of property. I was talking about those metals before, and those also steal photons with absorption. So that's just kind of a big picture of that. And then this is a solar spectrum. So if you were able to separate the sun into all of its wavelengths, this is what you would see. So these two lines up here in yellow, the two really dark ones, those are the sodium doublet. And those are ones that are very prominent and very present, so we use those a lot. And then we have the magnesium triplet, which is these kind of darker ones, 3 in a row, kind of in the center of the green region there. So that those are some features that we'll be using in our instrument to do kind of our science. But basically, all you need to know is that chemicals leave signatures at very specific locations that we know the wavelengths of, because thanks to chemists, they know the wavelengths of those exact transitions. So one more background thing is the Doppler effect. So you experience this anytime an ambulance will drive towards you and the pitch will sound high, and then it drives away and immediately it drops. So this is what happens when the source that is emitting this light is actually moving. So if you're on this, if the red dot is the ambulance and you're on the right side, you'll hear a higher pitch or a higher frequency. And then as the red dot passes you, you'll pass into this region here where the lines are spaced further apart, and that is a lower frequency or lower pitch. So what this looks like in kind of terms of that rainbow picture that we saw before is that these dark lines, these absorption lines, will actually shift according to the observer, depending on if that star is moving towards or away from you. So if it's moving towards you, it'll blue shift shorter wavelengths. And if it's moving away from you, it'll red shift longer wavelengths. So this is exactly what we use to see how stars are moving relative to us. So we know that this is what it should look like. We take a spectrum, we know that that sodium doublet is waiting for us. So if that shifts to the left, we know, okay, it's moving away from us. If it shifts to the right towards blue, then it's moving towards us. So this is just to give you an idea of what this looks like, the stream things and the impacts look like in velocity space. So don't let the numbers and stuff freak you out. The bottom axis there is just location in the sky, and on the left is velocity, kilometers per second. So you can see here all the stars, they're grouped around, for the most part, on the edges, they're grouped around the same velocities, they're moving. And then where you had that dark matter subhalo impact, you can see the effect of that on the velocity, and it does so in a very signature way. So it depends on the mass of that like little clump that's going through. So whether it's 1 million times the mass of the sun or 10 million times the mass of the sun, will have a different signature. And as you might expect, something more massive will have more of a signature than something not as massive. But the bottom kind of gives you an idea. The bottom, you're like, is there something there? Is there not? The top is definitely present. So that's where you have to be really careful with how powerful your instrument is to be able to see that kind of bottom case. Okay, so that's the background. That's the science part. And now I'm just going to talk a little bit about the project that I'm specifically involved on and the instrument I'm helping build. So this is VIA. This is an all-sky 5-year survey that will begin in early 2027, so not that far from now. We have 500 nights on 2 telescopes in the northern and southern hemispheres, and we're hoping to collect data for over 3 million stars. This is a collaboration between multiple institutions, Harvard and Smithsonian at the Center for Astrophysics in Cambridge, Carnegie Observatories, which is in California, Stanford, and Yale. So most of the instrument building and design is happening between Harvard and Carnegie. The actual build of the major instrument components will be happening in Cambridge. And then Stanford and Yale have a lot of amazing scientists that are doing a lot of important work on that side. So those 2 telescopes I was alluding to are here. We have the MMT, which is in Arizona. This is a 6.5 meter telescope. It's called the MMT because it used to stand for the multiple mirror telescope, but as you can see, it only has 1 large mirror now. So they just swapped it out and improved it, but kept the name, and now we basically only say the acronym, because the full name is a little bit confusing. Then on the right here, we have the Magellan telescope. This is a pair of telescopes that's located in Chile in the Atacama Desert, and these are also 6.5 meter telescopes. So you can imagine building 2 copies of the same thing, and taking advantage of the fact that the mirrors are the same size, the collecting light is about the same size, and you can observe both the things in the northern hemisphere and the southern hemisphere, because the skies are different there. So you can think of these basically as giant buckets, and then they're waiting to collect as many photons as possible. So our instrument will actually go in this the telescope dome in the back there for Magellan. Okay, so a little bit of an engineering diagram here. I'm going to dive into each of these components individually, but the big blue and white structure is the telescope. This is the Magellan telescope, the Magellan Clay telescope. That's the second one in the back. And you can see that the instrument has three main components. It has the fiber positioning system, the fiber chain, and the bench spectrograph that we call VSPEC. So first, I'll talk about the telescope. So these are the two domes that I showed you in that pretty picture on the right earlier in Chile. So on the left, you have the Bada telescope, and on the right, you have the Clay telescope. So Clay is actually where we will be mounted on, but you can see this giant primary mirror, 6.5 meters. A person is there for scale. Like, this thing is massive and huge. But you can see on the left a little bit more of the telescope structure, so that's what I'm going to spend a little bit more time on. This fancy bucket that we're collecting photons with. So here's a cartoon of the structure. You have the big primary mirror, 6.5 meters, a smaller secondary mirror up top. These baffles, which just help keep in the light, the science light that you're getting, and keep out stray light. And then the fiber positioning system, where you can think of like the focal plane. This is where the image is being made. The light rays are being focused. So to give you an idea of the light path, we have light that comes in to the telescope, reflects off of the primary, and comes down through the secondary onto the fiber positioning system.
You know how big the secondary is?
Not off the top of my head.
Fascinating.
Yeah, yeah, this is like a Cassegrain design. So let's talk about the fiber positioning system. So this is where the first part of the magic happens. This is the first thing after the telescope that the photons actually get to see. So on the right here, we have the cat of the whole thing, but the real magic happens with just this one small component that you see on the left. So this is a small robot. I actually brought one with me today, so I'll pass this around to play with. So you can see it's about, the size of 2 hands, pretty thin, and this allows us to position these fiber optic cables, same ones in telecommunications, to a specific star in the sky that we want to see in that stream. These streams are like multiple degrees on the sky. They're huge. So these fibers, they get pointed to a specific star, and then this robot has to move to find that star in that right exact spot. And because you're pointing the telescope at many different fields where the stars are in slightly different positions, this allows you to kind of be more flexible in that regard. So you can see this fiber optic cable coming out the back. It's about as thin as a hair. So just be careful with it. It is glass, so don't bend it too hard because then it'll break. But I put a red flag at the bottom, so hopefully no one pokes their eye out. Yeah, but you can see fiber optics are really magical. I'll explain how they work a little bit, but if you shine your camera light or point it up to a room light, you can see the other end will glow with light. So I'll pass this around. It has no electronics or anything. We made it like a dummy, so you can just pass it around. So I'll start it over. Yeah, there's 2 axes. There's an alpha and beta axis that just gives us a lot of room to point around. Yeah, so basically those robots are these little sticks right here at this part of the instrument. So this part up here monitors the atmosphere and gives commands on like how we can basically respond to the ever-changing atmosphere and the turbulent atmosphere. So the fiber optic light pipes the light down to this connector part, and then it continues to run out to the instrument where we get those rainbow pictures. So this actually is a video from the lab looking down into the robots. So this is like a mini mock-up that we have in the lab. And for those online, you can probably see that those robots have these green glowing dots at the tips of them. Those are the fibers. So we're backlighting them with green light, and then you can see them kind of focus on the tips. So they kind of dance around and move around depending on where we would want them to go to point at stars. So this is an image of what that actually looks like. So all the yellow dots are stars. That's where we're trying to go. And the robots have to be commanded to go find them. And they have to dance in this very special way because they can't collide with each other. The fiber optics are very delicate, so they do this really cool dance. So speaking of fibers, this is where I live. This is my specific area of expertise. So fiber optics are made up of these kind of three regions. We have the core, the cladding, and the buffer. So the core is just pure silica, it's glass. This cladding surrounds that core, and it has a lower index of refraction, which allows the light to propagate. If you don't know what that means, don't worry about it. Basically, it's this nice coating that keeps the light inside. Then the polyimide is this like plastic buffer coating, and that's just to protect the very breakable glass. And those are the rough sizes. So about a human hair size, 200 microns in the core. You can consider these basically magic portals for light. So light will come in on one side and exit the other side where the spectrograph sits. This allows you to not have your spectrograph on the telescope while it's pointing and moving around and shaking things and making your optics misaligned and all of that. But the unfortunate thing about fiber optics is there's a bit of a catch. So sometimes if the fibers aren't perfect inside, or if they're being stressed because of a mechanical stress or something, they actually increase the angle that's exiting the fiber. So if you know about like an F number or focal ratio, this is known as focal ratio degradation. So the input focal ratio is slower than the output. The output is faster. So basically what happens in the context of the instrument, one of the negative consequences is that your spectrograph, well, it's kind of hard to see. Your spectrograph is designed for some width of light here. So anything outside of that is just lost. It's thrown away. So you're supposed to be kind of seeing like a light faint yellow here on the outside. That's like the faster angle that's coming out there. So we just lose those photons, which makes us sad because we don't have many to work with to begin with. So my job is to mitigate that. So that's what I spent my first 2 years doing, but I won't spend too much time on it. But if you want to know more, that's specifically what I do. Finally, we have the spectrograph part. So you see all the fibers coming in, all 600 of them. They're in this, there's not 600 here, but there will be for us. We have this nice vertical, we call it the shoe, that aligns all of them very nicely. And then light exits out of them and continues on. So we're going to kind of flip over. So now that's going into the page. Imagine that going into the page there. So the light exits the fiber optics, hits this big mirror that we call it the collimator. This makes the light parallel. And then it hits that grating, that fancy CD that we were talking about. So what that does, right, light exits, goes parallel, the mirror just redirects it, and the grating separates it into color. So sorry, you can't see that super well up here, but online you might be able to see the different colors there. So it's making the rainbow for us. So this is what that actually physically looks like, not just a cartoon. So you have the fibers coming in up top here where it says fiber chain. Then you have this big collimator mirror. That's the biggest mirror we have in this setup. Then it hits a fold mirror. It hits that grating, which is like our CD. And then it passes through a bunch of lenses to carefully focus that light onto our detector, which is where we get to see the rainbow with all the lines missing. And that's what our grating actually looks like.
It makes the rainbows for hundreds of stars at once?
Correct.
Wow.
So when they're organized, right, so the fibers are in this vertical position. So the spectrum end up on the detector. There's a direction where the rainbow is spreading out. And then there's rainbows stacked like this, basically, on top of each other. So each row is a spectrum. And then you have like 600 of those at a time. Yeah. So it's just a kind of summary video of what's happening. So again, the telescope's collecting light, reflecting it up to the secondary, passing it down to all of our fibers and our robot sitting there. They pipe those light to the spectrograph. It's about 15 to 20 meters away. And then it hits, you know, this collimating mirror, fold mirror, and passes through, and we get our rainbow. So this is what the final step is. So we get this rainbow, and I cropped it because these are the wavelengths approximately that we're specifically interested in. There's a trade-off. You can't get the whole rainbow and get very good resolution, as we call it. So you have to kind of trade off between those two things. So this, think about this as like, if these lines could attach together and be one long continuous rainbow, that's what the camera is seeing in black and white, of course, no color. And then in the bottom, we basically create this version where we're looking at the intensity over all the wavelengths. So this is what we're looking for. And then as these lines shift left and right and we fit them, we can see how fast it's moving towards or away from us. So that's everything. That was a lot that I threw at you. So we talked about the telescope, how this all works, what we're actually trying to achieve here with our stellar streams and dark matter science, and how really precisely measuring the motions of these stars is going to enable us to figure out what the dark matter distribution is around the Milky Way. So I'll just let this video of the stream play while I'll happily answer any and all questions that you have.
All right, well, thank you. Let's start in the room. Is there a question? Yes.
Sure.
Under questions, question mark,
Mm-hmm.
that line, each of those lines that's coming down vertically is a star?
So this is actually one star's footprint
Oh.
that it's giving us.
Those are intensities, right?
Yeah, so this is the rainbow. This is the rainbow basically. So you have like yellow through green, and this is just giving you the intensity over that region. So it's that rainbow picture.
So what would hydrogen alpha look like?
So hydrogen alpha isn't in this region.
Sorry,
Actually,
so
it's in the
pick
red,
another-
but
Yeah.
you have the sodium doublet is these two skinny guys here.
Oh,
So they're absorbing some of the light and taking the intensity away. So that's why you see it.
I get
Yeah. So that's what
Phil?
you're looking at.
Is it possible that neutrinos are dark matter?
Yes, I have heard this as a potential theory, but I don't think it has been. I don't know if it's been confirmed or denied.
What was that question?
The question was if neutrinos are dark matter. I want to say no, but I don't have a study or anything to confirm that.
So it's
But-
possible.
I don't know actually. Maybe yes, maybe not. I think,
Well, that's possible.
yeah,
Um,
I don't think it's on that picture that I showed of theories, but it could be neutrino-like or some other kind of particle, yeah.
I've got a question.
the neutrinos that we've detected are would be a form of hot dark matter. They're too
Okay.
zippy. So people have talked about these heavier neutrinos called
Okay.
sterile neutrinos, which is kind of scary. But I don't think the case for it has been confirmed well at all.
Yeah, I would agree with that. That's my gut read of things, is that there's been papers put out and no one's come to counter argue them exactly, but it doesn't seem to fit well, at least with the leading theory. Yeah.
Okay, I have a question here.
Sure.
So I have a question regarding the fiber optics.
Yeah.
And how do you position them with because the accuracy, the need, and the actuation and everything needs to be in one just to get that.
Can you speak up more because we're
I can
putting in a
summarize it.
microphone there?
I can summarize it.
Yeah,
Okay,
that-
great.
Yeah. So the question was, fiber optics are extremely small. How do you position them accurately enough such that you can actually
For
get
the
the
same
star
star all the time.
for the same star all the time? Yeah. So there's multiple components that go into that. A lot of it is the telescope that is just trying to hold the position very accurately during your observation. Your exposures can be anywhere from like 30 minutes up to multiple hours, depending on how faint you're trying to go. So part of that is the telescope. The other part of it, which we're controlling, is the actual ability of the robot to get to the right place. So for that, we are relying on like micron accuracy. Because you can see how small that fiber is. You can barely resolve it with your eyes. So the fact that we have to get a star that's like, like hundreds of thousands light years away onto that small fiber is really hard to do. So for that, we rely on the Swiss, which are building our robots. You think of the small gears and motors that they use to make their nice Swiss watches. So those actuators are coming from there. So we're relying on them to have really precise motors to do that blindly. And then we also have kind of a metrology loop, which I didn't talk about, which we say actuators go here. They do their best first attempt. We actually image them, And then we see how well they did and then make corrections to it from there. Yeah. Sure.
Speak up.
Thanks for a great talk. I'm curious about the subhalos and this larger cloud of dark matter that we believe our Milky Way is surrounded by.
Yeah.
So if I call that a soup, you're basically trying to, tell me if I'm right or not, you're basically trying to figure out if the soup is lumpy or cream of celery.
Exactly.
And if it has matzo balls, how many big and little ones? I mean, will this actually let you say something about the distribution or relative likelihood of different masses of these dark clouds?
Yes, so as I kind of showed on that earlier plot where they had like the slightly different signatures, so we should be able to back out the mass of the object that the subhalo that would have interacted with it. We can also back out its orbit if we know it well enough, and its velocity and other information. But we're basically hoping that statistics will allow us to tell whether we're looking at a creamy soup or a chunky soup.
And to the date, we really have no handle on this question?
So we haven't been able to really like see these dark matter clumps or not, because they just you're not able to see them. They don't emit photons. They don't reflect them. They don't absorb them. So this is kind of the first survey that I know of that's really trying to do it on like a Milky Way scale and like actually do the statistics of mapping out like what these clumps are doing, because that's just a computer, and that gives us a good idea of what we might expect. But you can't let a computer, lead you. You got to go out and get the data yourself and see where it leads you. So we might observe all of these streams and see nothing, but that's also telling us something. That picture that the computer's making is wrong. So that's valuable too.
So let's come back to the room in a minute, but I know we have some people chomping at the bit online. Alan, did you have a question?
Well, I wanted to point out that somebody posted a question in the chat room, but also great presentation. I don't have any questions. You answered all of them, but I wondered if you could, whoever did that earlier, if you could put the fiber optic thing back up in the camera again. I didn't know.
Where is it?
Sure.
Anyway, thanks a lot.
Of course, yeah. This is the CR screen, but that's the robot. Yeah. So you have the fiber optic cable coming out the back. I have like a red piece of tape on it because it's so hard.
Yeah, I see it.
Yeah. So that'll actually extend like 20 meters, but it's just a short little guy for this. So you see like the silver part, and then the black part is the arms that are moving around.
Thanks.
Struggle it for you, wait.
Thank you.
That's okay. This one is for demos. Let's see if I can. Did you see the question in the chat?
Yeah, I had to make it go away. Hang on a minute.
I could also read it to you.
No, I'm reading it.
Oh, okay.
I mean, I'm biased to say our own survey, but yeah, you could say the particle. I think the particle physicists have kind of their own idea of what they think might be the best idea of kind of creating it or doing it with like a in the lab. But I think this, to my knowledge, at least working on the project, I'm definitely biased. Is one of the most revealing kind of experiments for the dark matter front, at least in this way, that you can see individual subhalos and isolating them and resolving those and tracking their orbits.
Okay, before we come back to the room, are there any other questions
Yes, I've got a question, of course. The fiber optic telescopes, are they primarily for the galaxy and the stars in the immediate area? You don't do other galaxy stars, do you?
Yeah, so for our instrument specifically, so I talked a lot about this dark matter science, but we're also doing many other types of science. And that includes like dwarf galaxies and other things, but all the stuff we're focused on is in the solar neighborhood. I think it's just because from the ground, it's kind of hard to resolve things on such small scales.
Yeah.
They're so dark. Yeah, but there's other surveys that are doing more cosmological things, like the DESI survey that's on Kitt Peak in Arizona. They're using fiber optics and they're doing more cosmological things. So, yeah, but we're focused mostly on the Milky Way.
Irene, can you tell us your question? All right, it's in the chat. Let's go there again.
I'm glad you know what a DVD is. You know the five and a quarter floppy?
Huh, yeah.
That's all.
I got some too.
If you had to guess me, what era do you think we'll actually have dark matter figured out? Well, I think it's going to be a while until we have it completely figured out, but I'm hoping we'll have a better sense at least of what the picture looks like in the next 10 years. So hopefully. Hopefully.
Anything else online?
And you can work on dark energy.
Yeah, then you got to move on to the other bigger pie slice.
Are there
Anything
any,
else online?
yes, do any of the funding cuts that we're all hearing about every day to NASA and to other groups, do any of those affect your project specifically?
Yeah, I appreciate that question. So specifically this project, no. I don't know if it was my advisor's gut or what it was, but we were actually able to secure private funding for this instrument. So we've secured over $20 million in private funding to date, which is great. We've been, using that as we work on getting the first final deliverable hardware in the fall, so we can really start actually building this thing. But something that actually did pop up like a couple of days ago are the tariff situation. So as I mentioned, our actuators are from Swiss, and I believe it's at 39% tariff currently. So that's going to be like $1 million tariff, which is not great. So we're just thinking about how to approach that. But I'm grateful that we haven't been slowed down or impacted by it directly. But we're closely monitoring the situation to see how that happens. So.
All right, we'll come back online before we go, but Mario's been very patient. What do you got?
A couple of years ago, I read a paper that dark matter was its own theorized to be its own antiparticle, and that it was an excess of a certain gamma ray coming from the center of a galaxy because it's denser there. It was presumed to be annihilation of dark matter, which, if true, would be the only non-gravitational detection of dark matter. Any more thoughts on that, or has there been any more data?
Yeah, unfortunately, I don't know too much about that. That's my short answer, but I'd have to point it to the dark matter experts on our team. Sorry.
Well,
Can we turn off the slide to the room?
This one you can answer.
Okay.
How closely packed can you get those fibers? In other words, could you turn it into an integral field spectrometer?
Yeah, so we actually consider doing that for our instruments because it's really nice for like dwarf galaxy science, which dwarf galaxies are these like small galaxies that are around. But we ultimately decided that we were able to get the fibers close enough together. They can, if you have actuators, they can collide, so they can actually reach, the neighbor ones can reach in and get them together, but they're not the fibers themselves are not going to be touching, like in an IFU, for instance. Okay. And that's because the robot has some size that it's holding onto the fiber. So the fiber itself is tiny, but it's in this like 1.5 millimeter ferrule, and then the robot grabs onto it, so they can't be touching. But we decided, for the dwarf galaxy science that we wanted to do, we could get them close enough that we'd be able to resolve enough stars in the dwarf galaxy to do some cool science. Yeah.
What's an IFU?
Integral field
unit.
Ah.
It's basically like you pack a bunch of fibers close together, and then you use it kind of like a detector in some ways. I know we have some more questions here.
Okay, how about, okay, yeah.
Have you been able to observe any of the stellar streams on other galaxies or only on our own?
Only on our own. Yeah, they're just too faint if we try to go.
You're special, I knew it.
I know. Milky Way. Well, hopefully, maybe one day, maybe from space. I don't know, but even then, it would be very challenging.
Think global, act local.
Yeah. Any other questions in the room? Yes.
Yeah, just wondering, given the mechanism, the fact that those ones are just capturing a tiny bit of light, despite the fact that it's a 6.5 meter scope.
Yeah.
Have the brainiacs in Cambridge kind of thought about harnessing the power of all the amateur astronomers and all the light that we gather via pictures or via our own eyes? Have we slap something up the back of telescopes that they could then harness all the data that comes from that and do the spectrometer stuff after the fact. It's a really big
Yeah,
data project.
I might need you to say that again. Do you mind
So,
rephrasing the question?
all right, given that the magic wand, the Harry Potter wands you have.
Yeah, so we'll have 600 of those.
Yeah, but they're
Yeah.
pretty small.
Yeah, they are
despite
small.
the fact that the mirror is 6.5
Yeah.
meters, right?
Correct, yeah.
Therefore, you could miniaturize that mechanism and just have a one wand type mechanism that could be potentially put onto the back of a lot of different telescopes.
Yeah,
Be it the big ones or even harnessing the power of the amateur astronomy community.
yeah.
You know, I remember watching my first presentation here, it was about 10, 15 years ago. It was the glass plates from the library
Yeah.
that were being scanned. And, you know, there's, every one of us hits a slice of the jigsaw and nobody puts it together. We should kind of try and figure out how to put it together. And that's a global project. Not just-
Yeah, no, I love a collaboration like that. I mean, I think fiber optics are really powerful because they allow you to just transport light wherever you want it to go.
And then you could have that, you gather the data, you wouldn't be reliant on the Swiss mechanisms coming over here.
Yeah, you need the bottle opener and the can opener and stuff, so you gotta have.
As long as it's not a Celestron.
Yeah.
Right, yeah, so I just want to point out, so this is kind of the side, so this little black part is like where we're kind of sitting. The primary area is much larger than that. So by the time you get to where we are, it's not as big, but it's probably about like this big, the whole focal plane with all the 600 robots really packed close. So you can imagine, you know, doing this. I think there's some telescopes where you can use like one fiber at a time to basically point at things, but there's no reason you couldn't do this for a smaller scale and have everyone do it. It's a little bit challenging to really accurately position that fiber just because it's so small and the stars are so small of what you're looking at. But there's been many projects to use those robots so far, so we're not the first. We're standing on the shoulders of giants, we're building off of them. So we hope that, you know, whatever we do and what we can accomplish, we can pass that forward to, you know, the astronomical community.
I hope the software is open source.
Yeah, I think that's the plan.
Thank you.
Yeah, of course.
Okay, well, last one in the room.
Okay.
I just wanted to point out from the perspective of someone who was in graduate school in the 1980s, even with the biggest functional optical telescope at the time, the 5 meter at Palomar, we got one spectrum at a time.
Yeah.
This is like having 600 telescopes. It's I just want to put the perspective there of the mind-blowing increase in the scope of the science that you can even imagine doing.
It's a lot of data, yeah. No, I appreciate that point. That's very true. Yeah. Each fiber is delivering a separate spectrum, a separate rainbow. So the fact that we can do 600 at one time is really great.
And all of them are getting, for that arc second, for that point on the sky, 6.5 meters of aperture.
Exactly. So we've got a big bucket. We're hoping to catch as many photons as we can.
And we used to just piss them away, sorry to say it that way.
I know, we're hoping to use as many of them as possible. Yeah, we're hoping the fibers are doing a good job of carrying all those photons to the spectrograph. And that's my job, is to make sure that no photons get lost, or as few as possible get lost in the fiber optics. Yeah.
All right, is there another question online? Aha! In the room.
Oh, we got one.
Do you have to use any special anti-reflective coatings on the ends?
Yeah, so each time you go from air to glass, you lose 4%. So you can imagine, you know, your tip of your fiber, you're going from air to glass there. So you can AR coat that to bring that down to about like 1%. So we're doing it there. And then we actually have, I think I showed in that like fancy, like the CAD model here. We're actually doing something kind of unique, which is that we have a connector, a fiber optic connector, which I have another example of I brought with me. So the fiber will come down, that one in the robot will come down and go into this like plug panel, which is shown in that like green there in the fiber positioning system. And then another fiber will come on the other side and meet it, and then this will run 20 meters into the spectrograph. So this connector, if you have two of them coming down, you're going from glass to air, air to glass. So it's another potential photon loss point. So my first 2 years, we're testing how to minimize that. We think we have this connector point down to about 5%, which is really great. I think previously most instruments were doing about 10 to 20%. So hopefully we'll improve there. And then, you know, there's some loss in the fiber, et cetera, that gets you to the end. That focal ratio degradation, that like broadening of the beam that I was talking about is another place. But yeah, AR coding can help you, especially at the beginning and then at the end as well.
I have a question.
Oh, sorry, could you say that?
Bounce and jitter?
Yes, yeah. Bounce and jitter we have to worry about. The telescope, it's huge, it's very heavy. We have to worry about it there. The spectrograph, we also have to worry about. It's sitting on this plate. As the telescope will rotate, it'll go with it. So there's these springs that isolate that movement and keep everything from shaking there. Yeah, so that's all important.
Quick question about air to glass.
Yeah.
What the distance between the air and the glass, or the end of the cable and the glass, how much air does it take to make that 4% degradation?
I think it's basically any amount of air.
Good.
Yeah.
Wow.
It's just anytime you change interfaces, yeah, because your like index of refraction or whatever is changing and other things. So.
All right, thank you.
Woo, thank you.
Nice job.
I have to tell you something. Hang on a second. Hang on a second. We got 37 in the room and 14 online. That's 51. That's a new record. So.
Yay.